Well, welcome to today's seminar. We're about to begin. Before we do, though, please be aware of the exit signs in case we need to leave on short notice. And having said that, for those who are at the website and on the internet, please be aware that you can send your questions in at any time. However, we would prefer if you send them in as soon as you can so we have time in the air to answer them. The address should be at the bottom of your monitor. So with that, Melanie.
Thank you all for coming to join us in person and online for this research seminar. My name is Melanie Zauscher, and I'm the contract manager for this research study. We're here today because California has committed to reducing greenhouse gas emissions, including our 2030 goal to reduce emissions by 40% below 1990 levels, in order to protect Californians from the impacts of climate change. Because the transportation sector is the largest emitter of greenhouse gas emissions in the state, we must understand household decisions to buy and drive cars in order to inform and correctly evaluate state policies that aim to reduce the carbon footprint of the sector. Today's seminar will cover the second half of the research contract, modeling household vehicle and transportation choice and usage, and will focus on understanding car purchase and travel at the household level. Specifically, this study examined the impact of the price of gasoline on household decisions regarding what car to buy or lease, how much to drive each household car, and ultimately their emissions. The effect that other cars in the household have on car purchase was also analyzed. The seminar for the first half of this study, which focused on factors found in households that own no cars or fewer than expected cars, was presented on April 24th. The seminar recording can be found on our website. The final report for this contract has also been posted to our website. This work is an important component of our broader low carbon transportation research, which supports ARB's efforts to reduce transportation emissions and to meet the state's air quality and climate goals. For more information on this research area and this research projects in this area, please visit our new low carbon transportation research portal listed in this website. Ta-da! The principal investigator of the study is Dr. David Rapson, a professor of economics at the University of California, Davis. His research focuses on vehicle choice and usage, the electric vehicle market, energy efficiency programs, and electricity pricing. With that, I'd like to turn it over to Dr. Rapson and look forward to your questions after his presentation.
Okay, thank you very much, Melanie. I'm here to talk today about three main research projects that were undertaken by Ken Gillingham, Chris Knittel, and myself over the last several years with the support of Melanie and the other research team here at ARB. I suppose I don't need to read the disclaimer, but these results are exclusively those of the authors, and Air Resources Board does not take any of the blame for things that are disagreeable. So the context of this research project is a suite of policies, ambitious policies undertaken by the state of California, many of which are administered by the Air Resources Board and led by the Air Resources Board to reduce the damages from pollution in California. These are both greenhouse gases and other types of pollutants. And this is a very complex setting. It requires a suite of regulations and other strategies that are intended to reduce these multiple pollutants and induce innovation. And it's within that context that this research is intended to make a contribution. So the motivation here is to help policymakers in California to gain a deeper understanding of how household vehicle purchase and usage decisions affect emissions. Our goal was to deploy the frontier empirical techniques to rich data sets that will allow us to retrieve credible policy relevant estimates of individual and household behavior. We also sought to push the methodological frontier in our vehicle choice modeling through the design of a dynamic model of vehicle choice. I guess I just want to also say one thing, which is I think it's commendable that ARB actually sponsors this type of research, because the policy is often ahead of the research, and policy decisions are made without the benefit of the research that follows as a result of that. And so I think it's an extremely valuable process, and I really commend ARB for sponsoring and making this type of research possible. So there are two main types of findings and accomplishments of this research. The first is the results themselves. We find that the emissions from high emissions vehicles decreases more when gasoline prices are high. And this highlights an important heterogeneity. Under these conditions, an optimal gasoline tax that accounts for differences across households is going to be higher than one that does not. So this tells us something. If we are to use a gasoline tax as a way to mitigate damages from multiple types of pollutants, this tells us something about the level that we would want to deploy. The research on household portfolio interactions finds that when households own multiple cars, there's a relationship between the attributes of those cars that is desired by the households. And in particular, when the kept car in a portfolio is made more efficient, the demand for the rest of the portfolio is going to be for less fuel efficient cars. And this I think has implications for fuel economy standards that we're still exploring. And then the final accomplishment, I would say, is that we developed and solved a dynamic discrete choice model of vehicle demand and usage. And this is definitely on the frontier of our knowledge, of our methodological capabilities. And as you will see when I get to that, we didn't quite get as far as we would have liked because it's very complicated, and there were several challenges that we had to try to overcome. So we wish that we had had more time and resources to push further, but this is the nature of trying to push the frontier on a complicated topic like this. So there are going to be three basic sections to this talk, each corresponding to these different research projects, sub-projects. And I want to just identify also the primary intellectual contributors to the work, because it's different on each project, and both in terms of attributing the intellectual ideas and content to the appropriate people, but also in terms of giving you a signal of which projects I'm going to be able to most deeply answer questions about. I want to just share that this first project on the co-benefits of gasoline tax was performed by Chris Knittel and Ryan Sandler, who used to be a graduate student at UC Davis. The household vehicle diversification project was with Ken Gillingham, Chris Knittel, and myself, and a superb graduate student that we have, Jim Arksmith, who also contributed immensely to this work. And then the dynamic discrete choice model, vehicle choice model, was with Ken Gillingham and myself. And we'll very quickly wrap up at the end. So starting with the co-benefits of gasoline taxes paper, as many of you know, gasoline taxes are almost uniformly promoted by energy and environmental economists as the best remedy, along with other things like cap and trade that assign a price to externalities, the policy that's promoted most by energy and environmental economists. And this paper tackles the challenge that is presented to this remedy, which is that if there are multiple social damages that are created by burning gasoline, then if we just are taxing gasoline rather than the damages themselves, it matters whether these other damages are correlated with gasoline consumption or if they're less so. So for example, greenhouse gases are almost perfectly correlated with gasoline consumption. The amount of greenhouse gas that you emit is going to be basically a per gallon function. whereas the other damages that are created by burning gasoline, such as local pollution, accidents, and even congestion, are much less perfectly correlated. And so this creates a complexity that will not necessarily be solved by simply taxing gasoline. Now, I don't want to dwell too much on terms, but I was told that I need to define all the terms that I use, and so this is my attempt to do so. But I just want to make a couple notes before we dive into the content. The first is that if I use the term externalities, which I will try not to do, what I mean is social damages that are created by a private choice but borne by people other than the decision maker. So climate change is a perfect example, but also local criteria pollutants. And the determinants of the social damage of local criteria pollutants are going to be both the concentration of those pollutants and where they occur, the population density that is experiencing exposure to them. Economists believe that pricing these damages is the optimal way to proceed, setting a price on the pollutant that's equal to the value of its marginal damage. That is the optimal Pigouvian tax. It is the benchmark against which we evaluate policies that seek to solve these problems. And most of this paper actually deals with the second best optimal tax. And the idea here is that because there are multiple social damages produced by driving, we might not be able to exactly tax each of those damages separately. In fact, it's inconceivable or infeasible that we would actually be able to do that. And so by promoting a gasoline tax, we're basically saying, okay, let's tax this thing that we know is correlated to a lot of bad things that we want to reduce. But the nature of that correlation is important. So if vehicles are very different with respect to the amount that they're driven as a function of gasoline prices, then that's going to have implications for what the second best optimal gasoline tax will be. If they do not differ in their sensitivity, then that also has implications. And that's exactly what this paper seeks to estimate. So we want to see, is there a correlation between the amount of miles driven as a function of gasoline prices, and then how does this map into the damages, specifically the local criteria pollutant emissions that are created? And then how well will a gasoline tax perform at reducing these social damages? Those are the questions that we're going to try to answer. The working horse data set that's used in this project is smog check data, which gives us measures every few years for every vehicle in California that is tested of the vehicle miles traveled through odometer readings and emissions rates of various pollutants. So that's going to be the main data set, and we're going to supplement that with gas prices and vehicle attributes. And the approach that we're going to take is estimating the response of vehicle miles traveled to changes in the gasoline price, changes in the cost of driving. And then we're going to use those to say, okay, what is the optimal tax? Were we in a situation where we could actually optimally reduce the damages created by the burning of the gasoline? Then what is the optimal tax to do so? We're going to then say, okay, what damages remain? And then we're going to look at what would happen if we were in a world where we could actually change the gasoline tax or change the remedy in order to take account for the differences between the responsiveness to gas prices of different cars. And the main model that we're going to estimate it's a regression model that has the log of vehicle miles traveled on the left-hand side, and we're going to see how how driving behavior is changed by the price per mile. So DPM is the dollar per mile traveled. So that's going to be a function of the fuel economy of the car as well as the price of the gasoline. And we want to control for a variety of factors that might also co-determine VMT. And so that's what you see with all those Greek letters to the right. We're going to include controls for the type of car, where it's driven, and trends in driving in general, such that we want to be able to interpret the beta coefficient on the dollar per mile term as an elasticity of demand for VMT with respect to the price of driving. And this is going to be a proxy for something that we would, as a policymaker, shift around by raising or lowering the gasoline tax. And what we find is that criteria pollutant emissions from dirty vehicles are more responsive to gasoline prices than those of cleaner vehicles. This is not something that I think I would have necessarily had a strong prior belief about, so this is an interesting finding. So dirtier vehicles are more price responsive, and what that implies is that the optimal gasoline tax, if we're going to use this second best gasoline tax as the way that we try to remedy local criteria pollutants as well as greenhouse gas emissions, then this result implies that that tax should be significantly higher than if we don't account for the differences between vehicles. We then look at the optimal but likely infeasible policy of taxing vehicles based on their actual emissions, and this can we show through this that a uniform gasoline tax can reduce less than 25% of the social damages. So this I think points to the complexity of policy that attempts to remedy multiple different social damages at once. Okay, on to the vehicle, the household portfolio project with Jim Arksmith, Chris Knittel, and Ken Gillingham and myself. So the question here is one about households that have more than one of a particular good. There's a question of to what extent the attributes of one good affect the desirability of attributes of the next good that is purchased. And typically this is something that is assumed away in vehicle modeling efforts. In large part, this is because the data are often not available. One of the key components that made this project possible was the data set that ARB helped to create that identified the households that were buying and selling these cars and was able to map individual cars to the same household. So you could essentially see when a household bought and sold cars. That's the type of data that we have for this. That is very rare. I've never heard of that type of data being available elsewhere, and it is because of the lack of availability of that data that we just assume that this is not an important feature when we being economists, when we model these settings traditionally, we assume that these types of household portfolio interactions are not important or don't exist, even if we acknowledge that they are important. So the policy relevance is that this is potentially going to be something that affects fuel economy standards. And with a acknowledgement that fuel economy standards, once again, were put into place as a kind of constrained policy effort to reduce pollution, it has also become quite clear that there are features of fuel economy standards that create incentives that will erode the benefits that are created by them. And today we're actually going to show that this is potentially another channel of erosion that we might want to be concerned about. So the data source that we use for this project is 6 years of household level vehicle holding. We have 22 million household transition observations. We're going to include smog check data that allows us to know how much vehicles are driven, a VIN decoder that matches VINs to vehicle attributes, and gasoline prices from Opus. The thought exercise that we have in mind here, and this actually took us quite some time to think about, to even figure out how to think about this problem. So we have, of course, households with many different numbers of cars and many different patterns of increasing or decreasing that number. And what we ended up isolating in this project is 2-car households that replace one of the vehicles. So the thought experiment that we have in mind is we want to consider one of these 2-car households. Were we to be able to do this, we would want to flip a coin and randomly drop one of those cars. We would then want to shift around the fuel economy of the remaining car and see how that affects the fuel economy of the car that's bought, or the fuel intensity of the car that's bought. So that's the thought experiment we have in mind. This is just kind of a diagrammatic way. We decide to keep the forward focus. What if we were to make it a little bit less fuel intense? Well, would that make the car that's purchased more fuel intense, or vice versa? That's the question that we're asking. Now, of course, if we look at observational data, we are not flipping coins to determine what car is dropped, and we can't actually think about experimentally shifting around the fuel economy of the car that's kept. So these are real concerns about whether we're going to be able to empirically retrieve the object that we want to here. And so we thought very seriously about this, and we ultimately came to a number of solutions. So the first is that we're going to look within households. We're going to look at households that have multiple replacement events. And the reason why this is important is if you look across households, you find that there are patterns that some households are exhibiting a preference for fuel economy that is exhibited throughout their portfolio. Some households prefer gas guzzlers. Okay, and if we were to look across households, we would say, okay, there's a strong desire for the same attributes within the portfolio. That is not the thought experiment that we have in mind. The thought experiment we have in mind, which we think is the appropriate one, is what happens within a household if you were to change the fuel economy. So deploying household fixed effects and looking at patterns within households that make multiple purchases is the right way to think about that. We also then developed what are called instrumental variable strategies. So basically, when you think about the non-randomness of what cars dropped and our inability to actually experimentally shift around fuel intensity of the kept car, instrumental variables provide us with independent variation that basically do that. That's kind of the layman's explanation what an instrumental variable does. And we're going to use 2 of them. One is the change in price differences between the vehicles in the portfolio are going to be predictive of which one is dropped. So to the extent that those are random with respect to the household, then that's kind of like flipping a coin in order to determine which car is dropped. And the second one is gasoline prices at the time that the kept car was purchased. There is a significant amount of evidence, which probably wouldn't surprise you, that the gas price at the time that a car is purchased influences the fuel intensity of that purchase. When gas prices are high, people buy fuel-efficient cars. When gas prices are low, they buy gas guzzlers. And that's basically the intuition. The timing of when people bought that Honda Accord in the past is going to tell us something about the relationship between past gas prices and fuel intensity. These next 2 slides are just intended to convince you that this relationship actually does exist. And so this one is a little bit, a little bit academic, I would say, but it's interesting enough that I want to show it to you. This is a graph of the probability. So the y-axis is the probability that the least valuable car in your portfolio is dropped. And the x-axis is the change in the unanticipated change in the vehicle values, the difference in the vehicle values up to the point when the car was dropped. So you can see that on the right-hand side of the x-axis, when the least valuable car is depreciating more quickly in an unexpected way, we're more likely to drop it. On the left-hand side, we're less likely to. So basically, changes in market prices of the cars that you hold are going to be predictive of which car that you drop. And we're going to assume that those are independent of anything relating to the household vehicle choice. And that's what makes this a valid kind of independent source of variation that brings us in line with our thought experiment. And then a similar graph can be shown here for the relationship between the kept car fuel intensity and the gasoline price at the time that it's purchased. So here we basically are partialing out a bunch of other things that are changing on the x-axis. So that's why you have both positive and negative gasoline prices. These are partialed of other covariates, but what you see is when gas prices are high on the right-hand side of that graph, we're seeing that people are purchasing less fuel-intense cars than when gas prices are low. And the results are shown here. So each of these graphs is basically showing the same qualitative story. So I'm just going to focus on one of them. What you really want to focus on here is our main specification, which is the household HHFEIV. So these black dots with the big error bars. And what these are showing is a preference for diversification. So the fact that those coefficients are negative, so the y-axis in all these graphs is the marginal effect of kept car fuel intensity on bought car fuel economy. And what we can see is that as you increase the fuel intensity of the dropped car, it's affecting, it's operating in the opposite direction on the kept car, right? So in English, that means that if we were to make the kept car more fuel intense, we're going to have exhibit a preference for a less fuel intense bought car. So these things act in the opposite direction. There's significantly more I could go into on this slide, but I will allow you to ask questions if you have them. So we then began to look at vehicle attributes, because our conjecture is not that people care exclusively about fuel economy, is that they care about a portfolio of vehicle attributes that are correlated with fuel economy. So we want to know, is this effect that we're seeing, this kind of diversification effect, operating through other vehicle attributes? And we can deploy exactly the same empirical strategy, just put vehicle attributes of the bought car on the left-hand side, and we can see what the effect of the kept car is on those. This is particularly relevant from a policy perspective, because fuel economy standards are linked to vehicle attributes throughout the world. There's I don't think a single country in the OECD that has fuel economy standards that are not linked to attributes at this point. And so if it's the case that this is that this effect that we've uncovered is operating through attributes, then this is going to have even more of an effect on how well these fuel economy standards are going to perform. And this table is essentially showing you exactly that. All of the negative coefficients in this table are demonstrations of the fact that when you increase fuel intensity of the kept car, you're decreasing the demand for a large bought car. You're decreasing the demand for weight of the bought car or engine displacement or power of that car. So this is very much saying that consumers are going to react to holding a less fuel intense kept car through vehicle attributes of the car that they end up buying subsequently. Okay, so why does this matter? How big is this effect? Should we care about this from a policy perspective? Well, we still have not nailed the perfect so-called counterfactual here. But what we have done is a thought experiment that is the following. So what we're going to do is we're going to decrease the fuel intensity of a kept car in our data, and we're going to allow the bought car fuel intensity to adjust according to the marginal effects that we retrieved that I just showed you. We're going to hold vehicle miles traveled fixed, and we're going to assume away within household VMT substitution, because we don't have we haven't yet understood that thoroughly enough to allow for anything else. And then what we do is we just look at what this implies for the gasoline usage for both cars by multiplying fuel intensity by vehicle miles traveled. And we retrieve the net change for the household portfolio in gasoline usage. Now, there are lots of other things that are going on in fuel economy standards that we are not modeling, so this should absolutely not be seen as a program evaluation. We just want to try to uncover the magnitude of the forces that we're estimating here and put them in terms of fuel economy in the portfolio. And these waterfall graphs basically show the results here. So if we were to save, the left bar is a savings of 10 units of gasoline from making the kept car 10% more efficient. That's going to induce a preference for less efficient bought cars that is going to erode between 3 and 5% of, or it's going to create forces that have a magnitude of erosion of about 3 to 5%, leaving us with significantly less total household gasoline reduction than we would have hoped. Okay, so that's kind of, we think that this shows that the effect is very large and something that we probably want to understand a lot better as we think about deploying fuel economy standards. So this is pretty novel research, actually. The approach that we use, the data set that we use, the instrumental variables that we deploy, these are all new to the, or at least some of them are new to the research. We find that two-car households prefer diversity of fuel economy and attributes in their portfolio, and that these preferences may exert a strong countervailing effect on fuel economy standards. Okay, and the final section of the presentation is the dynamic discrete choice model that Ken Gillingham and I created. So the motivation for this part of the project was that consumers are forward-looking. So I mentioned earlier that when gasoline prices are high, people are willing to pay more for fuel-efficient vehicles. That's because presumably they are taking into account of the fact that they're going to have a stream of expenses associated with using that car in the future, right? They're forward-looking, and this has been demonstrated in many papers at this point. The other feature that makes this setting what we would call a dynamic setting is that buying and selling cars is costly, and what I mean by that is there are non-monetary costs associated with the transaction, going out there and finding a buyer for the car that you're trying to sell, going out there and dealing with a dealership or searching for the car that you want to buy, finding the exact right car. These are what we call transaction frictions. And the reason why they're potentially important is when you make a decision today, the fact that you face frictions for changing the car that you own in the future means that car is going to stick around for a while. Okay, so it's not like we see, this is actually exactly the reason why economists believe we see households owning cars for multiple years. Right? You have new technology arising all the time. Why isn't there just a constant reshuffling of cars in the fleet? Well, it's because it's really costly to change cars. So the intention here was to make a model that would incorporate these features and allow us to predict the evolution of the fleet subject to this, what we believe is a more accurate description of the way that consumers operate and incorporating this feature of transaction frictions. So that was the intention. And I was asked to put in a flow diagram of how this model works, and to be honest, it's really difficult to describe this, but what I will say is the way that these models basically work is you specify a model of consumer behavior, and in our case, it's going to have the features that I just described, and then you take it to the data and you find the parameters on that model that make the model's predictions fit as closely as possible the behavior that you see in the data. And that's essentially what this flow diagram is describing. And I'm not sure that it's worthwhile getting deeper into it, but I'm happy to do so in questions afterwards or offline. So what did we achieve? Well, we designed this model, and we went through several iterations that, quite frankly, took a couple years to design and program the working model. We solved it in MATLAB. We estimated parameters that are consistent with what we saw in the data, and we ran some simple counterfactual simulations about what would happen when we change the fuel economy of new cars, when gasoline prices change, et cetera. We're not at a point in this model where we think it's ready to be used for policy. It still needs to be expanded. It still needs to be refined, and it still needs to be tested extensively before I would feel comfortable presenting results or allowing it to be an input to policy analysis. So I'm not going to show results right now, but we did make substantial progress on understanding how to model this. Some of the challenges that constrained our ability to bring this to completion to our satisfaction is that the computational burden of this type of model is extremely high, and it forces us to make simplifying assumptions that are undesirable. So there's this trade-off between how realistic the model can be and what the constraints of our computational burden is. We attempted also to include multi-car households in this model. That is another extremely difficult extension of the model that we ended up, after investing months in trying to figure out how to do this, we just said this is not feasible at this point. The main reason for that is when you think about the choice set that a consumer has when they're going and choosing one vehicle, the complexity of that problem is exponentially larger when you have them choosing two vehicles at the same time, right? If you really want to uncover the portfolio interactions between those, it becomes exponentially more complicated. So those are the types of constraints that we encountered. We certainly learned a lot, and hopefully this will end up feeding into research that at some point is going to be very policy relevant. We just are not at that point today. So to conclude, the co-benefits of gasoline taxes work essentially examines the differences across vehicles in their response to gasoline prices and the various pollutants that they are emitting. And we investigated what this implies for the optimal gasoline tax that we might want to deploy. And what we found is that this heterogeneity really makes a big difference. Dirtier cars are more responsive to the cost of driving, and this would lead us to want to increase a uniform gasoline tax. We also found that failing to account for the differences between vehicles means that we're really leaving a lot of the social benefit on the table. And I think my takeaway from this is we want to think about how to separately regulate or find remedies for the social damages from on the greenhouse gas dimension versus congestion, accidents, and local criteria pollutants. For the household vehicle portfolio project, we found that two-car households exhibit a preference for fuel economy diversity, and that this has potential implications for fuel economy standards, and it may delay the retirement of older gas guzzlers. And then finally, the discrete choice model, we developed it, we solved it. We are still not at the point of being able to present any policy simulations that we can share, but we think that this was an important advancement of the way that we think about the problem, and hopefully it's going to turn into something that's valuable to you guys in the future. So thank you very much. That's the end of my presentation. I just want to reiterate my gratitude to ARB for being willing to engage in this type of research. And I hope that it's an important part of the policy generation process. So thank you very much.
Hello, hello.
Oh, there we go.
Hey, I'm Kevin Esslinger, Data Resources Board. I was actually UC Davis grad student in transportation at in Sperling, so have a little bit of a insight into all this stuff. But I was curious about the footprint curb weight displacement perspective. I feel like that's even still kind of correlative to the actual vehicle attributes that people are going after, whether that be additional passenger capacity or cargo capacity or pickup truck functionality or something. Was there an approach that tried to go to those kinds of more market-based decisions rather than kind of these more esoteric, like people aren't looking for an extra 3 inches of vehicle length to increase the footprint, in their decisions. It's obviously just directionality of like, I'm gonna get a bigger car, So.
Yeah, so I mean, our attempt to do that is in this table are they still able to see the slides online? So in this attribute table, I think this was our attempt to first understand whether the effects on fuel economy diversification that we were seeing are operating through vehicle attributes, which I think is important primarily because of the attribute basing, well, both to understand consumer behavior in general, but also because of the attribute basing of fuel economy standards. So if what we see is that this is causing people to demand larger, if you increase the kept car fuel economy, and that's causing people to demand larger cars, then that's going to put us farther down the attribute-based fuel economy curve. So the actual potential amount of greenhouse gas abatement that we could achieve from that policy is going to be diminished somewhat by that. Now, our attempt at quantifying that is this graph. Now, you're right that each of these attributes is very closely correlated. So these are not separate estimates. Everything is, because there's so much correlation between these attributes and fuel economy, we don't want to say that this is, they care this much about footprint or they care this much about weight. But the overall effect is along the magnitudes that we're showing here. Does that help? Mm. People, I mean, they're not. Right. Yeah, I think what you're describing is a story that rationalizes exactly what we're showing. Yeah, that's completely consistent with the way we view it.
So getting at those kind of, I don't know if this would be the right terminology, but it's like a
discrete
leap.
Jump.
Yeah, a discrete jump, exactly. Is more of the reality, and it just happens to correlate with footprint and curb weight. So you're kind of like one step away from the actual decision. Is it too hard to go into the data of 21 million vehicles to look at the vehicle attributes? Because I know just as a person who's just interested in vehicles, it's hard to determine whether the old Toyota RAV4, when you purchase it, has the flip-up seat in the back, because it was a rare add-on, and that would influence, purchasing. But anyway.
No,
yeah.
I think that we could look at that. I think that would be interesting. We have not looked at it yet, but yeah, it takes a slightly different approach to look at discrete jumps, but we certainly could do that, yeah, and that would be interesting.
Because I mean, it's really, you know, cargo carrying capacity, whether you pick the seats up or the seats down numbers, you know,
Yeah.
maybe both to run the models, and then
Yeah.
pickup truck versus non-pickup truck, and then yeah, a number of passengers, 5, 6, 7, or 4, 5, 6, 7,
Yeah.
8.
Completely agree. Yeah.
We're going to take this question from the internet. From the results of part 1, when you say dirtier vehicles, what do you mean? Is this based on smog test emissions, and if so, which ones?
Yes, this is based on smog check emissions and yeah, and I believe that it's NOx and carbon monoxide and hydrocarbons. Yeah, but to be honest, I'm going off of what is written in the paper and written in the slides here. So I could certainly get more clarification on that if you need it.
Hi, Belinda Chan, ARB. Going back to the household portfolio section, can you elaborate more on how the offsetting effects go into the retirement decision? Because I guess I don't really see, they're obviously changing vehicles, so I don't know where you're getting the delay.
Yeah, that's okay. That's a really great question, and it is actually at the core of our challenge of trying to describe the complete kind of general equilibrium effects of what we're looking at. So the idea is as follows. Let's say we are to do what we've done in this thought experiment and decrease the fuel intensity of the kept car. Well, in our mind, that's going to happen through fuel economy standards. Okay? Fuel economy standards are going to change the composition of the fleet. They're not, it's not like the rest of the fleet is going to stay stagnant, right? So the question is, what happens when that kept car that's now more fuel efficient is exerting a force on the preferences of the household? Well, they're going to go to the market and they're going to try to buy a less fuel efficient car, right? If you believe our results, that's what they show. But fuel economy standards are constraining that, right? And so what we think the channel is going to be that kind of manifests here is that old gas guzzlers, right, which are going to be hanging around in this fleet until they're retired, are going to become more desirable. This is essentially going to shift out the demand for less fuel efficient cars. And so I'm not sure whether you're familiar with the paper by Mark Jacobson and Arthur Van Bentham that basically explicitly looks at the effect of fuel economy standards on longevity in the fleet or scrappage rates of gas guzzlers. But that's essentially the same mechanism we have in mind here. And that's what I meant by that comment.
Next question we'll answer is also from the internet. It looks like the portfolio effect is weaker if the bought car is used instead of new. Is this correct? And if so, any ideas why this is the case?
This is correct. Yeah. What we're seeing is a smaller portfolio effect for used cars. And it could be a number of things. It could be the difference in preferences between households that buy used cars and households that buy new cars. It could be the effect of the choice set of cars. So to be clear, what we're showing here, or what the sample that we're using to retrieve these results is households that have had 2 replacement instances where they then purchase a used car. So they probably have a used car already in their portfolio. It's possible that just the distribution of potential portfolios is going to have a smaller capacity for this take-back effect or this portfolio effect. So we don't really have any evidence for one of those or the other, but I think there are multiple potential explanations.
I was wondering about the effect of the household income on sensitivity to gasoline price. Maybe if you buy used cars, you're more sensitive to gasoline price than if you buy new all the time.
Yeah, that could be true. We, by the nature of our empirical design, where we're looking within households, we do not currently examine the results by income. What we could do is stratify the sample based on income and re-estimate this. I think that might be asking a lot of the data, but certainly, yes, I think your hypothesis is interesting and I share it, yeah.
In a two-car household, I understand the conclusion that when a household replaces a car with a more fuel-efficient car, it may keep its less fuel-efficient second car. Do you have any data on the vehicle miles traveled patterns that result within a household? That is, do the households continue to drive the gas guzzler as much as they drive the new fuel-efficient vehicle? Or do they shift to mainly drive the fuel-efficient vehicle?
We do have data on vehicle miles traveled from the smog check odometer readings. It's a coarse measure because we only get it every 2 to 6 years, depending on the nature of the smog check. We have examined this, and it is currently on my desk as something that we're trying to understand. I think it's very interesting, and I'm not quite ready to talk about it yet, but it's definitely important and something that we're looking into. I will say that it's because of the coarseness of the measure, we're a little bit concerned about kind of overextending what we can say about VMT, because I think a lot of the switching that would occur is happening at high frequency, and we obviously do not have measures in our data of VMT at that frequency. But we're very interested in this, and we completely agree that it's important. Melanie, there was a second. Is this a question at the bottom here? I think it's just an extension of the same one.
Yeah, this is Bill Dean at Cali, PA. You said a uniform gasoline tax can reduce less than 25% of social damage from car pollution. But wouldn't the percentage depend on how much that gasoline tax was?
No, because the main idea behind that paper and this result is that there are multiple pollutants at work.
Right.
And so when you set the gasoline tax optimally for one pollutant, it may be suboptimal for another. And so you're trying to find the optimal trade-off, but it's always going to be, a uniform gasoline tax is always going to be suboptimal in certain dimensions. And what that result says is it's very suboptimal. If you try to solve local criteria pollutant mitigation efforts with a gasoline tax, that's going to be where you also want to reduce greenhouse gas emissions. That trade-off is going to lead you to a very suboptimal outcome.
Another question from the internet. I see the effect of lower fuel intensity of the kept car on the fuel intensity of the second car. Is there any effect on the body type, whether it's a car, SUV, etc., of the second one?
Yeah, so I think this gets to the same question that was asked earlier. We could certainly look at that. I think that is a very reasonable explanation for what we see in our continuous regressions, but we haven't looked at that yet.
All right, there's no more questions in the room or coming from the internet, so we're going to thank Dr. Rabson for the seminar. And if you do have any follow-up questions, feel free to get in touch with me, Melanie Zausch, or you can find me on the seminar website. And thank you.
Thank you, guys.